Hello and welcome to Civil Engineering Mathematics A. My name is Eric Tune. I'm a lecturer in mathematics at the Central TAFE in Perth, West Australia, and I'll be your host for this series of 8 programs. Civil Engineering Mathematics A, or CE, Math A as we sometimes call it, is part of the Certificate 4 in Civil and Structural Drafting. Students who finish this particular certificate normally work as drafting assistants in engineering firms. You'll find, however, that a lot of students do this certificate as part of a diploma. To be able to do a diploma in engineering, you have to have this certificate behind you. And so Engineering Math A, or Civil Engineering Math A, is an integral part of any course in engineering, whether that's mining engineering, structural engineering, civil engineering, or even electronic engineering. Civil Engineering Math A has a lot in common, in fact, with a nationally recognized subject called Engineering Mathematics A. That's taught Australia-wide. In fact, there are many other subjects that are very similar to Civil Engineering Math A, and I've got those listed on the screen here. We've got that nationally recognized subject, EA002. It's also very similar to surveying and mining mathematics, laboratory mathematics, if you study that in TAFE. Even if you do some remedial mathematics, mathematics fundamentals for instance, you'll find elements in common, and finally environmental calculations. What is in this particular subject? Well, let's turn again to the screen. I've got that divided into 8 lessons, 8 programs. The first one will deal with measurement and mensuration. The second program deals again with measurement and mensuration. Mensuration, by the way, is the use of formulae in measurement. But in program 2 we'll make a start with geometry. In program 3 we talk about the geometry of triangles and quadrilaterals. And then in program 4 it is algebra, followed by more algebra in program 5. And in 6 we start with evaluating formulae. And in 7 it's straight line geometry straight line coordinate geometry, and in program 8 it is introduction to trigonometry. Now you notice that we've got these numbers in front of these units. They refer to National Vocational Mathematics Curriculum modules. Again, they are taught Australia-wide. Now, what do you need to succeed in this particular subject? Well, mathematics is a doing subject. You can't do the mathematics just by looking at a screen. What you need is a textbook, and you need to practice it. And the textbook is specifically written for this type of mathematics, the technical mathematics. It's by Blair Eldis and Keith Pentlin. It's called Mathematics for Technicians. It's the 4th edition. And it is available from WestOne Information and Sales. And you see the telephone number there on the screen, 9229-5252. So if you need to obtain that book, then please give that number a call, and they'll give you some information how to get it. Apart from a textbook, to succeed in this subject, you will need a calculator. Now, initially, simple scientific calculator will do. Later perhaps you might want to buy a graphics calculator. There are some important skills that you have to learn, and I've listed those again here on the screen. You have to be able to round numbers, and you use a calculator. You have to estimate an answer. You should always check what you have keyed in, very important. Know where your important keys are. And you have to be able to substitute numbers into a formula. The other thing is, if the instruction manual is very important. A lot of students tend to lose their instruction manual, and then they're lost. One calculator that is very useful for this subject is the Casio. Perhaps you can see that here. It's the Casio FX82TL. It's widely available. It's got all the important features we need for this subject, and those features I again have listed on the screen. The important keys are bracket keys. I hope you can see those. They are over here. We need a power key to raise numbers to a power. That's in the corner over there. Degrees, to change between degrees and radians, we need that later on, perhaps not necessarily in this subject. Then there's a memory key, M plus here, and another one is a change of sign key, very important on this calculator, that has brackets with a minus in there. And an exponential key you see here at the bottom. Thus, you need a good quality calculator, a scientific calculator. So what we've got a textbook, we've got a calculator, but of course you have to enroll as well. You have to, if you want to get official recognition for studying this subject, you have to be enrolled. There are assessment requirements, and your local college will be able to tell you what they are. Now, what will be the procedure for these 8 programs? We'll go through the material. I'll put some slides, as we call them, on the screen. There is a problem there, and you try to do that. If you are watching these programs on a tape, you can of course stop the tape and do the problem then. A bit more difficult when you watch these programs direct, but the problems are not that difficult. It's actually all introductory type mathematics, and with practice you should be able to succeed. And we'll make a start with program 1 shortly. Let's make a start with program 1. Now, program 1 deals with measurement and mensuration. Mensuration is the use of formula in measurement. The content of program 1 is as follows. We've got metric units, can talk about that, conversions. Then we look at some rounding. The theorem of Pythagoras, very important in area calculations, you'll find later. And finally, perimeter calculations. Well, let's make a start with that first topic in this program. It's about units, the metric unit system, Système International. They call it actually SI. And if you look at this, we have 7 basic units. One is length, that's the unit for that is a meter, a symbol M. We've got mass, the unit for that is kilogram. Then time, that's measured in seconds. And the current, that is to do with electricity, is measured in amperes. Now, there are some other ones, but we don't really use those much at all. Now, the nice thing about the metric system is that all the units are related to these 7 basic units. For instance, if you talk about a Newton, then that can be expressed in a combination of those 7 basic units. There are also conversion factors that relate these units. For instance, kilo means 1,000. We already know that. But there are some other terms used in engineering that you should be familiar with. Let's have a look at those. If we look at some large prefixes, as they're called, then the first one we come across is tera, with a symbol T, capital T. There's a giga, and you might have heard of a hard disk drive that has, for instance, 20 gigabytes. 10 to the power of 6, that means a million, is mega. 10 to the power of 3 is kilo. 10 to the power of 2, hecto, not used very much, and a deca as well. Now, those are units for large measurements. Now, there are also units for very small measurements, and I've got those listed coming up. We've got pico, that is 1 over 10 to the power of 12. That is symbol P. We've got nano, so you could have something called a nanometer. Micro, and that symbol you see over there is mu, is pronounced mu. And then milli, we're all familiar with, that's 1,000th. And then there's a centi, 100th, not used very much in engineering. And then we've got a deci, and that's hardly ever used. There are some very specific units. When the metric system was introduced, people were worried about having to express things in terms of 1,000 kilo. We were familiar with the British ton, and so some units were introduced in the Australian metric system that are quite specific. For instance, we talk about a ton at 1,000 kilograms, and the abbreviation there is a small t, and notice the spelling. And hectare, to use with area measurements, that's equal to 10,000 square meters, or 100 meters by 100 meters. And finally, we also use a liter, which is the same as 1,000 cubic centimeters. And the abbreviation for liter is capital L. Now let's have a look how we can use these prefixes in conversion problems. And I've got a problem on the board, and hopefully before the answer is given you are already able to give the answer. Let's have a look how that works. First problem I've got on the board here, or on the screen, talking as a school teacher, as you notice on the board, we've got a screen here. Convert 102 kilometers to meters. Well, pretty straightforward, because we know, of course, that there are 1,000 meters in every kilometer. And so if we multiply 102 by 1,000, or 10 to the power of 3, we get the answer as 102,000 meters. Problem 2, a little bit more difficult. That's the way it normally will go. We start with an easy problem and then get into the more difficult problems. Problem 2. Convert 268.5 micrograms to grams. Now, a microgram is 1/1,000,000th of a gram. So we're going to get a number with a lot of zeros in front, because we're going to get a very small number. Here we go. The conversion factor is 1 over 10 to the power of 6. That's the same as dividing by 10 to the power of 6. And as you can see, you get lots of zeros, because when you divide by 10 to the power of 6, as in this problem, that decimal point you see over there has to move 6 places to the front. And you have to introduce these extra zeros to be able to place that decimal point. Let's have a look at a slightly more difficult problem. Here we go. We've got convert 10.5 square meters to centimeters squared. When you convert squared units or cubic units, there is going to be a slight difficulty. You can't just, multiply by 1,000. You have to take into account whether it's a squared unit or a cubic unit. Typical problem here. We've got 1 square meter as 100 centimeters times 100 centimeters, so I'm already changing to the squared there. So that's going to be 10,000 squared centimeters. And then finally we want to have 10.5 square meters, so that number there has to be multiplied by the 10.5 to obtain in the end 105,000 squared centimeters. And that's the same the way it works in problem 4. We've got in problem 4 how many gigaliters in 531 cubic meters. Now a cubic meter is actually 100 times 100 times 100 cubic centimeters, and that makes it 1,000,000 cubic centimeters. Why do I change it to cubic centimeters? Well, a cubic centimeter, 1,000 of those make 1 liter, so I get 1,000 liters. And that's not a bad thing to remember, that 1 cubic meter is equal to 1,000 liters. We want to know how many gigaliters there are. Well, we have to divide by 10 to the power of 9, because the giga is related to 10 to the power of 9. But we've got already 1,000 liters, so it's really divided by 10 to the power of 6. And finally, if you work that out on the calculator, you get 0.00. You got again the decimal point moving 6 places to the front. Quite a difficult problem, that one. You might have to look at that in more detail and practice those sorts of problems from your book. Okay, let's have a short break and then we come back with rounding. Rounding is very important. There are in fact 2 methods for rounding, and the first type of rounding is what's called decimal place rounding. I've got the rule here there. If you have to round, say, to 2 decimal places, then you look at the digit to the right of the second decimal place. If it's less than 5, you do not change it. If it's greater than 5, you increase it by 1. And you always make sure that the digit you round is an even one. And that is written out here. So let's have a look at an example. It's a lot easier than just to look at this rule. I've got some examples here. Round 37.987 to 2 decimal places. That 7 is more than 5. That makes that 8 and 9, as you can see. The next problem, we've got to the nearest 100th. That means 2 decimal places. That 4 is less than 5, so that 8 stays. And if we have a situation like here where we've got a 5 and we have to round to 3 decimal places, then we'll want to make that 1 7 there at the end and 1 8, so that the last digit is going to be an even 1. The other type of rounding involves significant figures. In fact, I can fill a whole program about significant figures. It's perhaps best illustrated by means of some examples. I've got an example here where you're asked to find how many significant figures there are in 379087. Now, there are 6 significant figures. You just count how many figures there are. In the next one, that 0 is used to count people, so there are exactly 35,840 people. There are 5 significant figures in that measurement. In the next one, that decimal point there and those zeros, they are used to place the decimal point in position. They have nothing to do with the accuracy of the measurement, and so those zeros are not counted, and we actually end up with only 3 significant figures in that measurement. Very difficult topic, actually, significant figures. Let's have a look at another example. How many significant figures in 37.9 000 amperes. Those zeros at the end indicate an accuracy, and they are counted, and there are 6 significant figures there. In the next problem, we've got again those zeros involved. All of those are significant, so we should have 4 as an answer. But when it talks about approximations, then we only have 2, because that number really is rounded there. We've got 24,000 rounded, and so there are only 2 significant figures in that. You can see you really need your book to study this particular topic. Very difficult, actually, significant figures. The next topic is about the theorem of Pythagoras. That's a little easier. Let's have a look. What is the theorem of Pythagoras? You all have heard of that. When we've got a right-angled triangle, then the longer side, that is opposite the right angle, is called the hypotenuse. And when you square the hypotenuse, then you'll find that to be equal to the sum of the squares on those other 2 sides. Now, mathematically, that's expressed as BC squared is equal to AB squared plus AC squared. Sometimes it's written differently, because BC might be called little a because it's opposite angle A, and AB is called little b, and AC is called little c. So you might see it as A squared equals B squared plus C squared. Let's have a look at some typical problems involving the theorem of Pythagoras. The first problem here is where we want to find the hypotenuse, knowing those 2 other sides. We might have to do some rounding there. We have that the square on x is equal to 3 squared plus the 5 squared. Work that out to be 9 plus 25 or 34. Then you have to take the square root of 34, and you use your calculator, and then you round it to 2 decimal places, 5.83. Slightly more difficult problem here. Here the hypotenuse is known as 2.4, and we have to find that particular side, so we have to do a subtraction. When you do the subtraction, 5.2 squared, subtract 2.4 squared, put it in the calculator, make sure you use the brackets, and round it to the nearest meter in this particular case. That means 3 decimal places, because the units are kilometers. So this is really quite a difficult problem, as you can see. If the hypotenuse is given, indeed you have to do the subtraction. The next problem is more difficult even. There you will need some algebra, and of course we're going to do that later on in program 4. Here we've got a triangle. That value there is x. We know that side is 5, that is 8 meters, and we know also that AB is equal to BC. Now, how do we go about it? We let that AB side be x, and then from Pythagoras we know that dA squared must be equal to 5 squared, the hypotenuse squared, minus x squared. But we also know in the big triangle that dA squared must be equal to the hypotenuse squared minus AC. Now AC is, if that is x and that's x, must be 2x. See, here we get into algebra. When you work that out, then here we've got those two equations. dA squared must be equal to dA squared. In other words, 25 minus x squared must be equal to 64 minus 4x squared. If you square that, you get 4x squared. You have to perform some algebra. You get 3x squared as 39, x squared as 13 as a result, and then we have to take the square root to get the value for dA, and if you do that, then you finally get 3.5. Very difficult problem just to follow on the screen like that. You need to practice, of course, from your textbook. Okay, let's have a short break and then we move on to our next topic, and that is about perimeters. The last topic in this program deals with perimeter calculations. Now, perimeter is simply the outside edge of a particular figure. Officially then, it's the distance traveled in moving once around the boundary. Now, for a circle, that perimeter is called the circumference. And it's got a special formula which you have seen before. It's pi, which is about 3.14 times the diameter. Let's get straight into a few problems, some easy ones first and then some more difficult ones. Easy one first. What is the perimeter of this rectangle? Well, if it's a rectangle, this side there must be equal there, so that's 6, that's 6, that's 4, that's 4. So it's going to be 2 lots of 4 and 2 lots of 6. And as we see, that equals 20 meters. Don't forget those units, because that is in units of meters. Then the answer must also be stated in meters. Let's go into problem 2, a little bit more difficult. Here we've got a circle with a radius of 3.5 centimeters. That means that the diameter is going to be 7 centimeters. So we multiply pi by 7. Pi, of course, you can get from the calculator. You should use the pi on the calculator rather than 3.14. Working that one out, it comes to 21.9911, and that goes on. We have to round, it says here, to 3 significant figures, so we want 1 decimal place, and it becomes 22.0 centimeters. Problem 3, we've got an interesting problem because not many people know that. We know that the equator is about 40,000 kilometers long. What is the radius of the Earth? In other words, if you want to dig from here to the center of the Earth, how far do you have to dig? We can work that out now using the formula. Here we go. We know that the circumference is pi times the diameter. We know that the circumference is 40,000. We can now work out what the diameter is by dividing 40,000 by pi. We get approximately 12,732. If you now half that and round it correctly to 2 significant figures, you should get 6,400 kilometers. So that is the radius of the Earth, and that's how it is normally written, R with the little E at the bottom for Earth. In the last problem, we look at a so-called composite problem. Here we've got a trapezium. We can work out what the side there is by using Pythagoras, because if that's 3 meters, then that must be 3 meters. We've got that side as 4, so we know that the hypotenuse is 5, and then it's just a matter of adding 5 to 3 to 4 to 6 to get the perimeter as 18 meters. Careful again with those units. I hope that you agree with me that you have to practice problems of the type I've done here on the computer. The work is covered in chapter 3. Try to do all exercises up to the topic area. effect area will be covered in program 2. Well, I hope you found this program of interest. I'm looking forward to your company in program 2.